Well, hello and welcome. Made a video here to start describing the physics concept of work. Some you may have heard of before if you've studied energy, but if not, it's a very important part of your study of energy. I've kind of described it a little bit below. This is not really a definition, but I want to give you some idea of just what work means when we use it in the physics way. It's how we change the energy of something. We turn one form of energy into another form of energy, or sometimes we say we increase or we decrease the energy in something. And there's three important requirements for work to be done. I've outlined two of them here in my description. First, we're going to be talking about work involved with a force. Every time we get work done, there's a force involved. But that's just the start. We also have to have some motion. If there's a force without any motion, there's no work done. And there's a third requirement involving the direction. I'm going to get into that when I look at some specific examples. Just be careful, because the word work is used in lots of different ways in our everyday language, like I'm going to work, or this was a lot of work to do something, or maybe you're working on homework right now. But we have to be very specific when we define things in science, and this is just another one of those situations. If you want something to kind of relate it to, if you think about what impulse was, and we say, well, what is an impulse for? Well, wasn't that just to change the momentum of something? Usually it's to transfer the momentum from one object into the other. So work is kind of the same thing for energy. It's how we move energy or transform energy from one form to another. Let's look at some specific examples and see if that's helpful. Here's a case of somebody mowing the lawn with a lawnmower. So there's actually two forces here that would be doing work on the lawnmower. The first is the push of the person. So when you use a lawnmower, typically you push along the handle, down and to the right in this situation. But the motion of the mower is rightward. So if you think about what this force is doing, only the rightward part of the force has anything to do with changing the energy of the mower. It's actually trying to get it to move faster. Not trying to change the gravitational energy. There's certainly no springs here. And so only the horizontal component of the force contributes to the work. So when we calculate the work, I said there was a third characteristic, and it's all about that direction. So what we do is we look at the amount of the force that's in the direction of the motion. We call that just the component of the force in that direction. Here it would be F times the cosine of the angle between them. That force multiplied by the displacement that occurs during that motion is equal to the value of the work. This is a Newton times a meter, which is equivalent to a joule, which makes sense because if you're going to use work to calculate the change in the energy of something, you obviously have to have equivalent units. If you've been in a math or science class where you've used dot products before, you might know that this expression here can also be written as a special form of multiplication. In my class, we haven't discussed this yet, but when you multiply two vectors together, like force and displacement, notice they're vectors, and that's why we use these arrows here. There's two ways that you could multiply. So you actually have to be very specific as to which way you're using. This form we call the dot product. So we actually put a dot symbol in. There's another form known as a cross product, which we'll see not too long from now, but I don't want to get into that yet. So that would be how we would calculate the work done by this person as he pushes right and down on the handle. Now let's take a look at this friction force. The friction force is, of course, opposite the direction of the motion of the mower. So it will be leftward here. When we put that force into the work equation, we would, of course, have the friction force here. We would have the displacement moved while it was acting, but we would have the cosine of 180 degrees because the displacement vector and the friction force are 180 degrees opposite. That's going to give us a negative number. So I just want you to think about what that means. The negative number does not tell you the direction of the work. This is not a vector quantity. It simply tells you that you are decreasing the mechanical energy of the mower. And that's what is really going on here. The person is trying to increase the energy, and the friction is trying to decrease. And for the most part, while you're mowing, those probably just completely cancel each other out. and your mower stays with a pretty steady energy as it moves across level ground. Let's look at some other parts to see what else is interesting about work. Here's the same person, maybe he's going to work on Monday after the lawn is all mowed. He's holding his briefcase with a vertical force, but because there's no motion, in this example here, there is no work done. So this is interesting. This is different than your concept of work. You can hold something really, really heavy, but there's still no work done if you don't move it anywhere. Well, even if you do move it, there's not always work done. Here's a case where this upward force is still being exerted on the briefcase, but because the motion is horizontal, we have 90 degrees in between them. There is no component of the force that's in the direction of the motion. So we still have no work being done. That means his lifting force is contributing nothing to raising or lowering the energy of the briefcase. Perhaps he gets to the stairs. Let's look what happens here. So if he exerts an upward force while he goes up the stairs, then the displacement is at an angle like this. So again, we would take the component of the force that's in the direction of the motion. That would be this little arrow up and to the right. You see how it's a little less than the actual force he's exerting. That multiplied by whatever distance he moves up the stairs would be the work done during that climb of the stairs. Now maybe this is an engineering firm and they've got a clever way to get the briefcases back down to the ground floor. They put it on a cable and they attach it to a motor and it lowers it down by itself. So the cable would certainly pull up on the briefcase even though it's lowering, because cables never push. So we would have an upward force while the object is moving lower. So if we multiply those two together times the cosine of 180 degrees, because that's the angle in between these two, we again have a situation here with negative work done because we're decreasing the mechanical energy. So all kinds of different situations we can get. Let's look at one more way to do a work calculation. Actually, it's kind of two. We did this when we did impulse and momentum. Sometimes your force is not just a number that doesn't change. It's a changing force. It might be a function of some kind. So if we were to put this on a graph, not with time, but with position, this gives us a graph of force versus position. And by doing the area between that graph and the horizontal axis, we would get the work done during that motion. If we put it in calculus form, as we do over here, this multiplication takes the form of this times, and we just put a little dot here, and that's where the motion is, the little dx. But these are tiny, tiny little steps in the motion. And then when we sum up all the little force times the steps, that gives us the entire amount of work done between position x1 and position x2. So when you learn calculus, you know that these two forms are pretty much different ways of representing the same thing. So I think I'm going to leave it there. That's a pretty good introduction into what we usually see when we start our study of work and energy. There will be more videos, one on the dot product and one with how work relates to potential energy. There's a very close connection that I want you to know about that. But we'll save that for another video. Hope this was helpful. Thanks for watching. Bye-bye.